Hello viewers on YouTube. In this video tutorial, we are going to consider capacitor. So your first question would be, what exactly is a capacitor? By definition, a capacitor is an electronic device used in storing electric charge. A capacitor consists of two conducting material, which are usually metal plates, wrapped around each other. These metal plates are wrapped in the sense that they never meet. And for this to be possible, an insulator has to be in between the two plates separating them. This insulator could be anything. It could be vacuum, likewise can be an air. In fact, it could be water or oil. It could be anything. And generally speaking, we call this insulator a dielectric. Now, to understand how much charge a certain capacitor can hold, then you need to understand something called a capacitance. The capacitance of a capacitor tells us how efficient a capacitor can hold an electric charge, and also we can determine its magnitude. So, to determine the magnitude of the capacitance of a capacitor, then we would need, symbolically represented with C, so we would need the permittivity of free space if we are considering vacuum to be the dielectric in between the two conducting material. Then this must be multiplied by the area of one of these metal plates. Then we divide it by the distance between the two metal plates. This tells us the capacitance of the capacitor, which tells us how efficient the capacitor can hold an electric charge. So there's another form which we can determine the capacitance, and this is in terms of the voltage, which we call the potential difference, and the magnitude of the charge at which the capacitor could hold. So the capacitance can also be determined by taking the ratio of the charge and the potential difference. So C is also equal to Q divided by V. Now let's pay more attention to the first equation. This equation changes in structure depending on the dielectric that is in between the two material. Now, like I said earlier, you use this if the dielectric is a vacuum. Alright? In case you are wondering what the value of epsilon naught is, we call it the permittivity of free space. And magnitude is 8.85 times 10 to the power of negative 12. And its SI unit is Coulomb squared per Newton meter squared. I can see that. Perfect. Now, if it is now something else that serves as a dielectric, if it's not a vacuum, it is air, for instance, or water or oil, then to get what you are going to use in place of the epsilon sub naught, then you need to be familiar with what we call the dielectric constant, or also in other words, the relative permittivity. Alright, some textbooks will use K, while some will use the relative permittivity as epsilon sub R. So the relationship is such that K is equal to the permittivity of the material that is being used in place of the dielectric divided by the permittivity of free space. So in other words, the permittivity, the relative permittivity epsilon sub R is equal to epsilon sub M, permittivity of material, divided by epsilon sub naught, permittivity of free space. So depending on what you are seeing in your textbooks or what you are taught or what symbol is used, alright. But for this video tutorial, we'll be considering using K. Alright. So if we solve for epsilon sub M, which is the actual permittivity we'll be using, you would get K times epsilon sub naught. Note, we called K the permittivity and the dielectric constant, and that's also what we called the epsilon sub R. So in a situation whereby the insulator separating the two metal plates is something else aside the vacuum, then they must give you the dielectric constant of that capacitor. Am I communicating? So that's what we now use to multiply the permittivity of free space and then get whatever else you are asked to find. Before we begin going through some examples problem, you need to be familiar with the energy stored in capacitor. This energy is called the electric potential energy, and to find its value or magnitude, you need to be familiar with the symbol we use to represent it. So if I have it in red, we use uppercase U to represent the electric potential energy stored in a capacitor. And to find its magnitude, all we need to do is to take the half of the product of the magnitude of the charge and the voltage provided in that problem. This formula can be manipulated depending on how you want it, and to manipulate it, just solve for either Q or V using this equation that is highlighted and have it substituted right here. If, for instance, we want to have it in terms of Q, and we want to have it in terms of C and V, then we can solve for Q over here and have Q to be equal to CV. Then upon substituting CV as Q, then you will observe that eventually we have the electric potential energy stored in that capacitor to be equal to 1/2 CV squared. You can also do the same thing by solving for V using this equation and have it plug it right here. And let's see. So since the energy is measured in joules, alright. Now there's also the energy density. You can also be required to determine the energy density of that capacitor. So first, what exactly it is? The energy density of a capacitor is the electric potential energy of that capacitor per the unit volume. And basically what it helps us to do is that it helps us to know how strong the electric potential energy of that capacitor is. So mathematically we represent it with mu. So I can get rid of this. Mu, which is the energy density, is equal to the electric potential energy U divided by the volume of the capacitor. In other words, since U is equal to half QV or half CV squared, you can have it as half QV divided by the volume. In other words, can also be called the surface area multiplied by the separation distance between the two metal plates or conducting material. So just have all this formula noted down. The energy density is measured in joules per meter cube. And this is the difference compared to the electric potential energy of the capacitor. Perfect. Now, just I forgot is the unit of the capacitance. The capacitance is measured in farad, which is written for short as F. Alright. However, there are some other ways in which the units can come, which is just to make things complicated for you. And before you could do anything, you have to have it being expressed in the appropriate units. So what exactly are they? The capacitance can be given to you in millifarad, 1 mF. In fact, it can be in microfarad, 1 μF, or nano, that's 1 nanofarad. And finally, it can be 1 picofarad. If it is a milli, to convert millifarad to farad, you multiply it by 10 to the power of -3 farad. And if it is a micro, we multiply with 10 to the power of -6 farad. And if it is nano, we multiply with 10 to the power of -9 farad. And if it is pico, we multiply with 10 to the power of -12 farad. So please make sure you are conscious of that. You watch carefully before you begin substituting or finding whatever you are required to find. Then the next thing I have to put into account before we go over some examples is the nature of the capacitance, as any of the quantity at which it relates would be if any of these quantities actually changes in value or magnitude. So now, notice that the capacitance is proportional relatively to the area of the metal plate. This means that if the area of this plate increases, then the capacitance will also increase. However, if the distance between the two metal plates increases, then the capacitance, let me use a different color for that so you can keep track of that. If the distance increases, then the capacitance will decrease. Please keep that in mind. As area goes up, capacitance goes up. as distance goes up, capacitance goes down. Now, what about relative to the voltage and the magnitude of the charge? Since the capacitance is also proportional to the magnitude of charge, it tells us that if the charge actually increases in magnitude, then the capacitance will also increase in magnitude. And if the voltage increases in magnitude, then the capacitance will decrease in magnitude. So that's what you actually have to be familiar with as well in anything relating to capacitance of a capacitor. Now, to make all this into good use, let's go over some examples for you. Example number 1. The parallel plates of a 1.0 farad capacitor are 1.0 millimeter apart. What is their area? So let's write out what we know and then figure out how we can determine what we don't know, which is what we are required to find. So we have the capacitance. C is 1.0 farad. The fact that it is farad, it means it is an appropriate unit, so we need not to touch it. We are also given the separation. I said the two metal plates are separated by a distance of 1.0 millimeter. However, this distance has to be in meter, so we need to divide it by 1,000 in order to have it in meter. So therefore, 1 divided by 1,000 is simply 0.001 meter. And that's perfect enough. So what formula would help us to determine the area of one of these plates? Well, this is how we're using C equals to epsilon sub naught multiplied by A divided by D. In case you might be wondering, why would it be epsilon sub naught? Because it's not specified. If it's going to be something else, then it must have been specified that the insulator in between the two metal plates is not a vacuum, but something else. Then the dielectric of the insulator used must have been given. So therefore, we are going to consider it to be a vacuum. So if that is the case, we can now isolate A. To isolate A, we can multiply both sides by D and have C cross D to be equal to epsilon sub naught times A divided by D again cross D. Now you see that at the right hand side, the D cancels out, and then we have CD to be equal to epsilon sub naught A. Now upon dividing through by epsilon sub naught, we can eventually have our area to be the product of the capacitance and the separation distance, and eventually divided by epsilon sub naught. Earlier, I gave you what the value of epsilon sub naught is, so we can have it substituted at this point. C is 1 and D is 0.001. Epsilon sub naught is 8.85 times 10 to the power of negative 12. And have this into our calculator, provide the final answer. So fraction 1 times 0.001 divided by 8.85 times 10 to the power of negative 12. So I got the area to be equal to 1.13 approximately times 10 to the power. So let me count the shifts: 1, 2, 3, 4, 5, 6, 7, 8 to the power of 8. So is this area, we have it in meters squared. So that gives us our answer to example number 1. On to example number 2. The plates of a parallel plate capacitor in vacuum are 5.00 millimeter apart. Now you can see this problem is a little bit more precise. Let us know that the insulator separating these two metal plates is a vacuum. So it means we are still going to use a formula similar to the one we just used. However, let's proceed more forward. 5.0 millimeter apart and 2.00 meters squared in area. A 10.0 kilovolt potential difference is applied across the capacitor. Compute the capacitance of the capacitor. So, what should we do? Let's write out what we know. So we have the value of D to be 5.0. More often, it's usually in millimeter, so be always conscious of that. Don't use it directly, you have to make sure you have it in the appropriate units. So this is the same as 0.005 meter. Excellent. So we have the area A to be 20.2, about 2.0 meters squared. 2.00, 2.0 the same. We have the potential difference V to be 10 kilovolts. However, we need it in volts. So multiply by 1000 to have it in volts. And that gives us 10,000 voltage. Perfect. So we need the capacitance C equals question mark. So which should we use? Since we have no charge, then we can use C equals to Q over V. But we can use this. We can use C equals epsilon sub naught multiplied by A divided by D, because A and D are actually given. And we know what epsilon sub naught is. So now let's determine the capacitance. So we have 8.85 upon substitution times 10 to the power of negative 12 multiplied by 2, which is the area, then divided by 0.005, which is the distance between the two metals. So fraction 8.85 times 10 to the power of negative 12, again multiplied by 2 and divided by 0.005. Alright, so I got 5.4 or 3.54 0.54 times 10 to the power of negative 9 farad is a capacitance. Excellent. However, this is 10 to the power of negative 9. Remember, you can have it as 3.54 times 10, no more 10, just 3.54. Then you said nanofarad. You know what the nano is already. Perfect. 10 to the power of negative 9. Excellent. And that gives us the solution to part A. On to part B. Determine the charge. We are also required to compute the charge on each plate. So how can we determine that? Since we have the capacitance already to be 3.5 times 10, 2.54 times 10 to the power of negative 9, we can determine the charge. Remember that the capacitance is still equal to the charge divided by the voltage. We do know what the voltage is. So upon isolating Q, we have Q to be equal to CV. Earlier, we said C is 3.54 times 10 to the power of negative 9. And the voltage, we got that to 10,000. If we do this product, upon computing it, this 10,000 will reduce the 10 to the power of negative 9 to 10 to the power of negative 5. And then we have 3.54 times 10 to the power of negative 5. Excellent. That's our charge. It is a charge that has been measured in coulombs. And that's it. On to part C. Compute the magnitude of the electric field between the plates. So pause the video and figure this out. What do you think we can do to determine the electric field intensity? If you could recall vividly from our knowledge in electric field, the relationship between electric field, the distance, the separation distance, and the potential difference, which is the voltage, is such that the voltage is equal to the product of the electric field strength and the separation distance. And upon isolating E, we can eventually get E to be equal to V over D. We have all these two quantities available in this problem, so it means we are good to go. So upon substituting the value of V, which is a 10,000, with the value of D, which is simply 0.005, and then let's have it into our calculator. So 10,000 divided by 0.005. So I got 2 million, which is the same as 2 times 10 to the power of 6. Its electric field is measured in Newton per coulombs. That gives us our solution to this problem. On to example number 3. Feel free to subscribe to this channel if you find it helpful. Also, you can always leave a like in order to tell YouTube that the video is interesting, so they can recommend it to many audience out there. The potential difference between two large metal plates is 120 volts. The plate separation is 3.0 millimeter. Determine the electric field between the plates. By now, I believe you should know what to do. pause the video and determine the solution to this problem. And after that, you can unpause it and see if you have done the right thing. So we have the voltage V to be 120 volts. And then we have separation distance D to be 3.0 millimeter. And upon having it in the appropriate unit, we have it to be 0.003 meter. Okay, for those who may be wondering, we have divided the 3 by 1000. So now we need the field strength. Earlier we said E is V over D. Upon substituting, we have 120 over 0.003. And I would need my calculator for that. So fraction 120 divided by 0.003. And I got 40,000, which is the same as 4.0 times 10 to the power of positive 4. So it is field strength measured in Newton per coulombs. And that's it. On to example number 4. Determine the charge on each plate of 0.050 microfarad capacitor when the potential difference between the plates is 200 volts. We have the capacitance C to be 0.05. I don't need to repeat that other 0 that follows 5. It's useless. So 0.05 farad. Well, it's a microfarad. Let's do that again. Microfarad. Excellent. So we need to have it in farad. So therefore, we need to multiply the 0.05 with 10 to the power of -6. And in fact, let's have these get rid of. And therefore, we have our final answer to be 5.0 times 10 to the power of -8 farad. That makes sense. So you just add these 2 zeros to these other 6 zeros we have to come before 5. Perfect. Now we have the voltage V to be equal to 200 volts. How could we determine, or how can we determine the magnitude of the charge according to the problem? Well, are you thinking of what I'm thinking? What formula do you think we can use? Excellent. We are using C equals Q over V, where Q will be equal to CV. And so therefore, for substituting, we have 5 times 10 to the power of -8 multiplied by 200. And let's see what that is. So 5 times 10 to the power of -8. I got 6 earlier, then multiply by 200. So this should be 8. And then we have 1.0 in standard form times 10 to the power of -5. So that's our solution to the magnitude of the charge. On to example number 5. By now, I want to believe you should have been developing your interest and understanding in capacitor. Number 5. Calculate the capacitance of a capacitor consisting of 2 parallel plates separated by a layer of paraffin wax 0.50 centimeter thick. The area of each plate being 80 centimeter squared. Full stop. The dielectric constant for wax is 2.0. If the capacitor is connected to a 100 volt source, calculate the charge and electric energy stored in the capacitor. Well, they said energy, but you know that it's the electric energy. Typically the potential energy. Okay, electric potential energy. Perfect. So what do you think? If you want to try, you can always try that. Let's begin by writing out what we know. Okay, so we are given the separation distance. That is simply the thickness of the insulator. So D is 0.5 centimeter squared. I said squared. 0.5 centimeter. And this is the same as 0.005 meter. You know, millimeter to meter you divide by 1,000. But when it comes to centimeter, you divide by 100. So 0.5 divided by 100 gives us 0.005. If you are not used with this, the 0.005 I'm using is 0.5 divided by 100 is the same thing as 0.005. Am I communicating? So that's how it works in Excel. Now, what is our given? We're given the area of one of these plates. A is simply 80 centimeters squared. Now, you have to be careful here. Alright? Converting the area to meters squared, you don't have to divide by 100. You want to divide by 100 times 100, which is 10,000. Very, very important. It won't make sense. We having it as 80 centi squared meter squared. Does that sound real to you? So that's why it's being pronounced as 80 centimeters squared. However, the centi too is also squared. So getting rid of it, you have to get rid of it as if you are getting rid of centi squared. So you have to square what its value is going to be, or what its value is. And its value is 100. So squaring 100, we have 10,000. So we are dividing this 80 by 10,000. And so therefore, we will have 0.0008 meters squared. Excellent. And there should be 2 zeros anyway. But perfect. So 0.008 meters squared. Perfect. We are moving forward. Now we have the dielectric of the wax. That's simply 2. So the value of K is simply 2. It's unitless. If you could recall, I said K is equal to the permittivity of the material divided by the permittivity of free space. If these two things are the same in terms of units, they will cancel out and would have the permittivity constant to be unitless. That's it. Perfect. So that's just 2. Now we can proceed on determining the charge and the energy stored. But before we could determine the charge, we would need the capacitance itself. So C is simply epsilon of the material multiplied by the area of the plate, then divided by the separation distance. Okay. Now the epsilon sub m that we are talking about is the permittivity of the wax. You know, we're given the dielectric of the wax, but we need the permittivity of the wax to get the capacitance. The permittivity we have been using right from the previous examples is the permittivity of free space, which is the permittivity of a vacuum. Am I communicating? But now the insulator that is separating the two metal plates, it's not a vacuum, but another insulator, which is wax. Perfect. Now we said K is equal to epsilon sub m over epsilon sub naught, and epsilon sub m eventually we showed that earlier would be the product of the dielectric constants and the permittivity of free space. So we have 2 times 8.85 times 10 to the power of negative 12. And what would that be? Let me use my calculator. 2 times 8.85 times 10 to the power minus 12. Alright, I got 1.77. 1.77 times 10 to the power of negative 11. Excellent. So that's what I'm going to be using as E sub m. Now let's substitute. So we have 1.77 times 10 to the power of negative 11 multiplied by A is 0.008 divided by D is 0.005. Perfect. Again, onto our calculator. Fraction 1.77 times 10 to the power of negative 11 multiplied by 0.008, then all the way down we have 0.005. Perfect. So in standard form, our final answer is simply 2.832 times 10 to the power of negative 11. It is capacitance for that. So that's simply the capacitance of the capacitor. Now that we have the capacitance, we can determine the charge by using Q equals to CV. Excellent. So we're out of space. Let's get it on some stuffs. I think this is useless at this point. We don't need that anymore. So let's have that in yellow. So since Q is equal to CV, it implies that we have 2.832 times 10 to the power of negative 11 multiplied by the value of V, that's 100. So the 100 will just reduce these to negative 9. So we have 2.832 times 10 to the power of negative 9 And if you could recall, we can also have capacitance to be compressed. Sorry, the charge magnitude to be compressed depending on how small and how large it is. So 10 to the power negative 9 represents the nano. So instead of it to be in coulombs like this, we can have it as 2.832 nano coulombs. Excellent. So that's the magnitude of the charge. The next thing is to determine the electric potential energy stored in the capacitor. So what do you think that will be? We explained that earlier. Let me just get rid of this to have enough space. We said the electric potential energy U is equal to half QV. Well, both value of Q and V are given, and Q is not given, but we have it already. Let's proceed on using it like that. So half times Q is 2.832 times 10 to the power negative 9, and V is simply 100. And let's plug in values and see what we have. So fraction 2.832 times 10 raised to the power negative 9, alright, multiplied by 100, then all the way down divided by 2. So I got 1.416 times 10. Well, the calculator does not give me in standard form, so I have to count the zeros. So I have, that's 7 to the power of negative 7. Perfect. So it's the charge, is the energy, we have it in joules. And that's our solution to example number 5. By now, I want to believe it should be being used to how to approach problems involving capacitor, regardless of how the structure of the problem is. Let's consider one more example before we end the video. So please, I want you to pause the video and try this example yourself. On to example number 6. A capacitor consists of 2 metal plates separated by an air gap of 0.05 meter. Each plate are of dimension 60 centimeter by 40 centimeter. When it comes to dimension, you don't read that clause as times or multiplication. You read it as by. Alright, it's a dimension. It's telling you, it's connecting the length, breadth, and height of a certain shape. Continuation. If the capacitor is connected to this should be 2, that's a typing error, to a 14-volt battery. Option A. Find the capacitance of the capacitor. As we have been doing, let's write out what we know. So we have the separation distance D to be 0.005 meter. Well, good news. We now have the first problem that gives us the separation distance in the appropriate units. Perfect. Now, we are given the dimension of this plate as 60 centimeter by 40 centimeter. When you're given dimensions like this, the first value is always the length, the next one is always the breadth. If it's up to 3, then the last one will be the height. Well, we know that area in geometry is simply the product of length and breadth. So, but both length and breadth are in centimeters, so we need to have them in meter. So I wouldn't need to write the conversion rate, but instead write the actual value. So that will be 0.6. When we divide 60 by 100, it becomes 0.6. Multiplied by 40 by 100 becomes 0.4. Perfect. So let's do this product and see what the result is going to be. So 0.6 for those who might be confused, multiplied by 0.4, that's 0.24 meter squared. Excellent. So what else are we given? If the battery is connected to a 14-volt battery, so we have the voltage to be 14 volts. What will be the capacitance? So C will be equal to 1. Well, we are still using the first formula we discussed at the beginning of the video, which is the epsilon of the material multiplied by the area of the plate divided by the separation distance. This time around, the insulator is here, so we would need the permittivity of air. So we were not given the dielectric constant anyway. It means you're expected to know what it is. So you can just check out Google or any platform to get the list of the dielectric of some insulator that is often used to separate the 2 metal plates. Though most problems usually state it out, but some problem would actually expect you to know what the value is going to be, more especially if it is air, water, glasses, or so. So for air, the dielectric is simply, let me just write K sub A. So K sub A was very, very close to 1, where some people usually even approximate it to 1, but we want to make it different from vacuum. Alright, we want to make it different from vacuum, so that's why we won't have to use 1. Okay, we won't have to use 1. So that's the actual value, 1.00059. So that's what we are using. So to get the epsilon sub m, this means we are multiplying 1.00059 with 8.85 times 10 to the power of negative 12. So what would that be? Let me use my calculator for that. 1.00059 times 10 raised to power negative I'm not type 8.85 times 10 times 10 raised to power negative 12. Excellent. So I got 8.86 approximately times 10 to the power of negative 12. So it's very, very close to that of vacuum, but we just need to have something slight difference to show that we are not using the same material. So therefore, we can have C to be 8.86 times 10 to the power of negative 12 multiplied by the area is simply 0.24. Then the separation distance is 0.005. Again, our calculator fraction 8.86 times 10 raised to the power of negative 12 multiplied by 0.24 and all the way down divided by 0.005. And finally, I got the capacitance of this capacitor to be simply equal to 4.252 times 10 to the power of negative 10. This is a capacitance, so we have it in farad. So that's our solution to the capacitor, so the capacitance of the capacitor. On to part B. In part B, we are to determine the energy stored in the capacitor. So how could we do that? Let's get rid of this to have enough space. Okay. So we said the energy U is simply equal to half QV. But we don't have the charge this time around, and we don't want to find it. We don't have the charge yet, and we don't want to find it. So let's just use C equals to Q over V, and then since we know that Q is equal to CV, well, we actually showed that earlier. We know that the U is the same as half CV squared. So we have these two values. We can make use of them instead to get the energy. So we have half times the value of C, because that will be 4.252 times 10 to the power of negative 10, and the value of V is given as 14. Excellent. Again, on to calculator. So fraction 4.252 times 10 to the power of negative 10 multiplied by 14 and all the way down divided by 2. So I got 2.98 times 10. Well, how many zeros? That's 9 zeros to the power of 9 joules. So this is the energy stored in the capacitor. And up next is the energy density. Perfect. Remember, energy density, it tells us how much energy the capacitor can actually store. So mu is equal to U, which is the energy, divided by the volume. Okay, the energy is simply 2.98 times 10 to the power of negative 9, not 9 anyway, divided by, to get the volume, like I said, is simply the product of the cross-section area, which is the area of one of these metal plates, and the separation distance. So the volume is the same thing as the product of A and D. So the area is, when we have it being converted, we got it to be 0.24, and the separation distance is 0.005. So let's plug in everything and get our final answer in no time. So fraction 2.98 times 10 raised to the power negative 9 divided by 0.24 times 0.005. Excellent. So I got 2.5 approximately times 10 to the power of -6. Alright, so in terms of units, the energy density is measured in joules per, so the volume is in meter cube. So that's our solution to this problem. And that's how you can easily solve problems involving capacitor. I hope you find this video helpful and useful. Thanks for your time and thanks for watching. See you in the next video. Bye for now. So I have an exercise for you which you can use as a practice problem. Feel free to share your solution with me if you are in the comment section below. Thank you once again. Bye for now.